Okay, this video accompanies the 1-7 presentation on writing two-column proofs. Some of our new vocabulary. A paragraph proof is basically a logical, 3, 4, 5 sentence paragraph explaining how you know or how you reason from a set of given facts to the conclusion. We're going to focus on two-column proofs. Once we're pretty competent with two-column proofs, they can easily be turned into paragraph proof form. A proof is a logical argument that reasons from a set of given facts to a conclusion connected by logical steps. And the two-column proof will supply the step to go with each, or the reason to go with each step that we make as we reason from our givens to what we need to prove. A theorem is a conjecture that can be proved. It's a conjecture. Some other things that we will use are what we call corollaries, which are results from theorems that don't need to be proved. And also we have postulates, which are things that can't be proved. One example would be the parallel line postulate, which is that parallel lines always stay, in plane geometry, parallel lines always stay the same distance apart. We can't prove it. That's a postulate. A two-column proof looks like this. We have there's two columns. We have a statement column. We have a reason column. We make like a T-chart. And we have, usually our given is number 1. So we'll be given some information. And we're going to be asked to prove something. So our given would normally go here, and then we have to logically reason to our conclusion, and our to prove should normally be the last step in the proof. So every two-column proof basically should have this form. We've got a given set of conditions that they give us. If there's not a diagram, we need to supply one. So let's say we have a diagram that looks like this. And we may be asked to prove something about like these angles or about segments bisecting each other or whatever, but we'll be given some basic information to start with the diagram. Or if not, we need to supply one. And then we need to kind of think logically about how we can reason from our givens to what we need to prove. And we do it formally in two-column form. And the way the paragraph proof kicks in is at some point when we're comfortable with this, we can easily turn these into a dialogue and just kind of reason through the sentences and put those together in a paragraph form. Okay, let's look at the next page. So here's our critique and explain, which is like the explore reason. This is the 5.1 that's in your student companion. So William solved an equation for x and wrote justifications for each step. So let me turn this into a two-column proof. So these are the statements. These are the reasons. This is his first step. So his first step, this is the given. 6 times the quantity 14 plus x is equal to 108. That's given. What did he do for step 2? He multiplied 6 times 14 and 6 times x. He used the distributive property. So notice that he did the work, and then step 2, his supporting reason is, What did he do? He used the distributive property. How did he go from 1 to 2? He used the distributive property. Step 3, he subtracted 84 from both sides. Subtraction property of equality. Step 4, he simplified. He did 108 take away 84 and got 24, so he simplified. And then in step 5, he used the multiplication property of equality, which means he multiplied both sides by the reciprocal of 6, which was 1/6. If he looked at this as dividing both sides by 6, the supporting reason would have been division property of equality. So as we look at him solving the problem, we can see what he did each step and what the supporting reason that allows each of those steps was. So part A, are his justifications valid at each step? This seems to be a logical series of connections. If we put 4 back in here, 6 times 18 is 108. You got 6 times 10 and 6 times 8. 6 times 10 is 60. 6 times 8 is 48. They add up to 108. So his justifications are valid. So there's nothing to change on that. Part B, can you justify another series of steps that result in the same solution for x? Well, I think there might be another way. What if instead of multiplying and using the distributive property, what if I just divided 6 out of everything and simplified it that way? So let's do an alternate proof. So we've got our statement reason columns. Step 1 is the given. 6 times 14 plus x equals 108. That's given. For step 2, though, I'm going to divide both sides by 6. So we end up with 14 plus x is equal to 8 is equal to 18. And what did I do to go from 1 to 2? I divided both sides by 6. That's division property of equality. Or division is good enough. Then for step 3, I'm going to subtract 14 from both sides. So x is equal to 4. So what did I do to go from step 2 to 3? I subtracted 14 from both sides. That's the subtraction property of equality that allows me to do that. And here we have basically found that x is equal to 4 for this problem. It took us 3 steps. Williams' method with his simplify step took 5 steps. One proof is just as good as another. It isn't how short your proof is. It isn't how long your proof is. The idea is that every step that you make has a logical reason or supporting reason for it, and no steps are skipped. Somebody should be able to follow through step by step exactly what was done in the proof. Okay, let's move on. So our essential question is, how is deductive reasoning used to prove a theorem? We reason from some given information. So from given information, now that information may be straight out listed as the given part, or it may be included in a diagram that accompanies the problem. And we reason from given information to some desired conclusion, which is our to prove. And again, the number of steps doesn't matter. The order you do things in, well, the order matters, but as long as you have logical reasons, like with the case before, William decided to use distributive property. Another way to do it would have been to start out by dividing everything and simplifying the numbers that way. So as long as different people will do their proofs in a different order depending on what they see, and but generally, proofs need to follow a logical sequence. Okay, let's look at what we need to do for theorem. Now our theorem 1-1, we call the vertical angles theorem. It's really important that you really don't, the way that these proofs are numbered in geometry generally is like 1-1 means that this theorem is from chapter 1, and it's the first theorem in chapter 1. The next theorem, if we're still in chapter 1 when we come up on our next theorem, which is coming up soon, would be theorem 1-2. Then we'd have theorem 1-3. As we move into chapter 2, the first theorem is going to be theorem 2-1. The second theorem would be theorem 2-2. So the numbering of the theorem basically tells you where in the geometry book that theorem occurs or comes up. Different geometries do things in a different order. Their theorems are going to be numbered differently. But in general, all geometries are going to at some point have a theorem called the vertical angles theorem. So it's important that you remember the name of the theorem when you use it. The theorem number doesn't really matter. It's not going to make any sense to anybody else that's taken a different geometry, but everybody that takes geometry should recognize the vertical angles theorem after they've studied it. So here we have a diagram, and here's our diagram. We've got two lines that intersect each other, and notice that these lines that intersect each other make a set of 4 angles. Angle 3 and angle 4 we call vertical angles, and angle 1 and angle 2 we call vertical angles. Vertical angles share a common vertex, and the sides of the angles are shared. Like the lines that make up angle 3 are the same lines that make up angle 4. The lines that make up angle 1 are the same lines that make up angle 2 on the other side of the vertex. So we need to prove that angle 3 and angle 4 are congruent. And then as a byproduct of that, we can argue that angle 1 and angle 2 must also be congruent. Okay, conceptual understanding. So this starts our proof. We want to write a 2-column proof for the vertical angles theorem. A theorem is a conjecture that's proven. Prove the vertical angles theorem. So they're giving us information. Line AE and DC form a pair of angles, ABC and DBE. They also form these other angles, but we're going to focus on these. So we want to prove that those two angles are congruent to each other. So let's see how they did this proof. They note that angle ABC and DBE are vertical angles. That's our given. And then they note that if you take angle ABE, which is angle ABC and angle CBE together, they make a straight angle. So they're noting that the measure of angle ABE is 180 degrees, and the measure of angle DBC is also 180 degrees. So they're talking about these vertical angles. And the reason that we can say that they're 180 degrees is because those are straight angles. This is the definition of straight angles. Now, some geometries might have you make a note that angle ABE and angle DBC are vertical angles, and then from that, you can say that their measures are 180 degrees. Step 3, the measure of angle ABC. Let me mark it up. The measure of angle ABC plus the measure of angle CBE equals the measure of angle ABE. And also, so here's ABE, and also the measure of angle DBE added with the measure of angle EBC equals the straight angle DBC. And that's our angle addition postulate. Now, since the measure of angle ABE is 180 degrees in step 2, and in step 3 we can see that the measure of angle ABE is the same as the measure of ABC plus CBE. We can substitute 180 for the measure of ABE, and that's what they did for the first part of step 4. So ABC and CBE add up to be ABE, but ABE is 180, so it got substituted in. 180 got substituted in. Same thing for DBE and CBE. Together they add up to be DBE by the angle addition postulate, but they're also equal to 180 degrees from step 2, so the 180 got substituted in. So a lot of times I will, when I do a substitution, to make it clear, I'll add in parentheses like 2 and 3. So this, when I read this, I see, okay, I did substitution and between steps 2 and 3. So anybody that's looking at my proof, if they see substitution, they can look at 2 and 3, and they can try to figure out, or they can figure out how the substitution worked, or where the number came from. So that's our step 4. So let's move on. So here we have that the measure of ABE is 180 minus the measure of CBE. So they're getting the measure of ABC by itself. So they're subtracting the measure of CBE from 180 from both sides. And they're going to do the same thing for the DBE, CBE part. They're going to take CBE away from both sides. So the measure of DBE is going to be 180 minus the measure of CBE. And that's subtraction property of equality. You're taking away the same thing from both sides. You're taking the measure of CBE away from both sides. Subtraction property of equality. Now notice that in step 5, ABC is equal to 180 minus the measure of CBE. And DBE is equal to exactly the same thing. Using the transitive property, since both of these are both equal to 180 minus the measure of CBE, I can actually use the transitive property and set those equal to each other. So that's what went on between step 5 and 6. So I might make a note here with the transitive property, go back to this, that steps 5 and 6 were combined together to give us that the measure of ABC is equal to the measure of DBE. So we've got these two angles equal to each other, and by definition of congruence, then these two angles are congruent. If you have two angles that are equal in measure, they're congruent. That's our definition of congruent angles. So we have, let's check and make sure that we did what we were supposed to do for this. We were supposed to prove that angle ABC is congruent to angle DBE. We started with these vertical angles in the diagram, and we logically, step by step, reasoned to the conclusion that angle ABC is congruent to angle DBE. So an old school way of showing that you checked your work, or that you're sure your proof is correct, like I said, it's 3 dots or a little triangle at the end. We're done. I did it. Okay, let's move on. So here's our try it. This is actually, we will save this and we'll do this in the student companion. Let's look at example 2. We want to apply the vertical angles theorem. So this diagram shows how glass lenses change the direction of light rays passing through a telescope. So the light rays are coming in. This is actually what we call a refractor telescope. A refractor telescope uses a lens and it focuses it through the focal point and then goes through the eyepiece and basically into your eye. A reflector telescope, the light comes in, bounces off a mirror up to another mirror, and then through the eyeglasses. So a refractor telescope actually needs to be longer than a reflector telescope. So this is a refractor. A trivia fact, I guess. Now, let's see what they're saying here. What is the value of x, the angle formed by the crossed outermost light rays through the focal point? So we can see that this is 11 degrees and this is 11 degrees. Together, this whole angle is 22 degrees. And by our vertical angle theorem, this angle x must also be 22 degrees. Here we have the common vertex. Here's the line that forms one side of the angles, and here's the line that forms the other side of the angles. These lines make an X. These two angles have to be congruent. If this angle is 22 degrees, this angle also has to be 22 degrees. Now we could easily figure out that these other angles are going to be 180 minus 22, which is going to be 158 degrees if we needed to do that. Because together these need to make a straight line, which is 180 degrees straight angle. Okay. Example 2, try it. We'll do in the student companion. Here's our next theorem, Theorem 1-2, congruent supplements theorem. So in general, so let me highlight this. So the congruent supplements theorem, with a little bit of a different wording, basically says that if two angles are congruent to angles that are supplementary, then those angles have to be congruent to each other. So see how that works. If two angles are supplementary to congruent angles or to the same angle, then they are congruent. So sort of like in regular speech, okay, two angles that are supplementary add up to 180 degrees. And so let's say we have one angle like this. Let's say we have another one like this. And let's say this is say it's a 60-degree angle, which means this has to be 120. Over here, we're going to do the same thing. This is a 60, this is 120. So if two angles are supplementary to congruent angles, so let's say we're talking about this 60-degree angle here. This 60-degree angle, call it angle A, is supplementary to this angle B. Together, they're supplementary, which means they add up, two angles that add up to be 180 degrees. So A is supplementary to B. Now over on this other side, angle C is the same thing as angle B. It's also 120 degrees. And its supplementary angle, we'll call it D, has to be 60 degrees. So we can see that, like if this 60-degree angle is supplementary to angle B, and if angle D, let's say we didn't know what angle D was, if it's also supplementary to either angle B or an angle that's congruent to angle B, which is angle C, which is 120 degrees, since it also has to make a straight line, it also has to be 60 degrees, which means that angle A and angle D are congruent to each other. So that's pretty much what this proof is about. So here's our given information. If the measure of angle 1 and angle 2 is 180, and the measure of angle 3 and angle 2 is also 180, we need to prove that angle 1 is congruent to angle 3. This is our to prove. Okay, let's move on. Okay, so example 3, we'll prove this in example 3. Let's look at our next theorem, the congruent complements theorem. This is really the same as the congruent supplements, except we're dealing with complementary angles, which are angles that add up to 90 degrees. And here we have angle 1 and angle 2 add up to 90 degrees. Angle 3 and angle 2 also add up to 90 degrees. So we can argue that angle 1 must be the same as angle 3. As an example, let's say this was a 50-degree angle. If these are complementary, if 1 and 2 are complementary, 1 must be 40 degrees. If angle 3 and angle 2 are complementary, then to make 90 degrees, angle 3 must also be 40 degrees, and we can see that angle 1 and angle 2 must be congruent to each other. So this is our to prove part. This is our given. And this is proved in the example 3. Try it. Let's move on. Okay, here's our example 3. We're not going to focus on paragraph proofs right now, so we're going to skip example 3. Basically, once you're comfortable with the 2-column form and the logical series of steps, it's pretty easy to turn those into an ordered set of sentences that basically works through the proof in paragraph form. Here's the try it that goes with example 3. We have theorem 1.4. All right angles are congruent. This is something we've kind of already been using, but this is our theorem 1.4. All right angles are congruent. So we know that angle A, since these lines are perpendicular, this makes a right angle, and we know that a right angle measures 90 degrees. Over here at angle B, we have another perpendicular situation here, which means that this is also a right angle, and it must also be 90 degrees. And since 90 is equal to 90, we can say that the measure of angle A is equal to the measure of angle B, which means that angle A is congruent to angle B. So this is exercise 9 in our problems. Theorem 1.5. If 2 angles are congruent and supplementary, then each is a right angle. I don't know how useful this one is, but it's our theorem 1.5. So let's say we have 2 angles that are congruent, which means that they're equal to each other. Let's call these x's. So each of these has a measure of x degrees. And if they're supplementary, that means they add up to 180 degrees, because supplementary angles add to 180. So if we add these two together, we have x plus x must equal 180, which gives us, if we simplify, 2x's equals 180. If we divide both sides by 2, x must be 90. So each one of these angles must be 90 degrees. So there's a short algebra series of proof in algebra, 3 or 4 steps, that basically proves that these 2 angles must be 90 degrees. And by the theorem before, if an angle measures 90 degrees, it must be a right angle. This is our proof part. This is our given. And this is done in exercise 11 in our problem set. Theorem 1.6, our linear pairs theorem. If we have a linear, now a linear pair of angles, we maybe need to review this definition. A linear pair of angles are 2 angles that are adjacent to each other that make a straight angle or add up to 180 degrees. Well, the theorem, now we've been kind of using that, but now if you have a linear pair, you know that they're going to add to 180 degrees. So here I have a linear pair of angles. What makes these a linear pair, and this goes back to earlier definitions from this chapter 1, 2 angles that share a common side that makes them adjacent, and their other sides are opposite rays, which generates a straight line, which makes a straight angle. Now, a straight angle has a measure of 180 degrees. This linear pair of angles must add up to 180 degrees. So if angle 1 and angle 2 form a linear pair, which means they make a straight angle, And since a straight angle measures 180 degrees, we can say that angle 1 and angle 2 measures must be 180 degrees. So here's our given. Here's our to prove part. And we'll go through this in exercise 11. Okay, let's look at our example 4. Write a proof using a theorem. So first off, notice that they're not given the theorem number here. They're using linear pairs theorem. And if we don't know what linear pairs theorem is, we need to go back here and look. And it says the sum of the measures of a linear pair is 180 degrees. So it's very important that we learn the names of the theorems and what they say rather than the actual number of the theorem. Like if I wanted to be a little bit more detailed, I could go back up here and I could say, well, the linear pairs theorem, that's theorem 1-6. So I might want to say 1-6. But linear pairs theorem is the important thing to put in for your reason, because other geometry students are going to hopefully know what the linear pairs theorem is, not what theorem 1-6 is. So let's reason our way through this proof. We're given that the measure of angle 1 is equal to the measure of angle 2. So I want to mark that on my diagram. And the measure of angle 1 is 105 degrees. And we want to prove that the measure of angle 3 is 75. So let's see how this is going to work. Since angle 1 is congruent to is equal to angle 2, we know that angle 2 must be 105 degrees. And since angle 2 and angle 3 are a linear pair, they must add to 180 degrees. So angle 3 must be 180, take away 105, which gives us 75 degrees. So that's the reasoning that's going to be brought out in this proof. So let's see how they did it here. Bring this up a little bit. Let's see. So measure angle 1 congruent to is equal to measure of angle 2 given. Measure angle 1 equals 105 given. Now a lot of times we can combine these two givens in one step. Like that. You can put all your givens in one step. Sometimes it's useful to do that. Sometimes it's confusing to do that. So it's, either way that makes sense is the way to do this. They tell us that the measure of angle 1 is 105. That's given. And from that, since angle 1 is equal to angle 2, if angle 1 is 105, we can say that angle 2 must be 105. So we have angle 1 is 105, and angle 2 is also 105. The transitive property leaves angle 1 and angle 2 equal to each other. So that's the transitive property of equality. That lets us say step 3. Now we note from the diagram that angle 2 and angle 3 make a straight angle, which means they're a linear pair. And that's the definition of a linear pair. Since they're a linear pair, they add up to 180 degrees. That's from our linear pairs theorem, which we just talked about. We've already kind of been using the straight angle equal 180 anyway. Now we have a theorem that says that for us. Now, since angle 2 is 105, we can in step 6, we can substitute 105 in for the measure of angle 2 in step 5. So actually what's going on here with the substitution property is we're doing substitution between 4, 5, and 3. So we're using steps 3, 4, and 5 together to end up with step 6. Next, 105 is going to be subtracted from both sides, which leaves the measure of angle 3 equal to 75 degrees. and that's the subtraction property of equality. So we were given that angle 1 was congruent to angle 2, or equal to angle 2, and that 1 was 105. We can kind of see how the proof went. 105 is equal to 105. These are a linear pair, which means they're 180. 180 take away 105, leaves us 75 degrees. So notice how the flow of the proof basically follows the math you would need to do to basically find the measure of angle 3, except it's in an order, a logical order with supporting reasons for each step. Here's our try it to go with example 4. And here we have our concept summary. Proofs use given information and logical steps justified by definitions, postulates, theorems, and properties to reach a conclusion. If we're given that angle 1 and angle 2 are vertical angles, we want to prove that angle 1 is congruent to angle 2. So let's think about how we would do this now that we have these theorems under our belts. Here we have two lines that cross each other and make two sets of vertical angles. Angle 3 and the other angle are vertical, 1 and 2 are vertical angles. So we note that angle 1 and angle 2 are vertical angles. Angle 1 and angle 3 must add up to 180 degrees because they're a linear pair. Angle 2 and angle 3 must also add up to 180 degrees because they're a linear pair. That's step 2. Since 180 is equal to 180, we can substitute. This also might be the transitive property. If angle 1 and 3 are equal to 180, and 2 and 3 are equal to 180, 180 basically joins us together, and I would actually think 3 should be a transitive property. You're using the 180 to link these together. So see, notice that substitution and transitive are really close to the same thing. To be substitution, they should have basically said like 180 is equal to 180, which would be reflexive. And then on the left-hand 180, they could substitute in measure of angle 1 and angle 3. And the right-hand 180, they could substitute in angle 2 and angle 3 and end up with step 3. That would be with substitution. But this is really transitive property. You're using the 180 to link the two together, and it leaves them that way. That's basically transitive property, not substitution. They're going to take away measure of angle 3 from both sides, which leaves measure of angle 1 equal to angle 2. Subtraction property of equality. And if two angles measures are equal, then they must be congruent. Definition of congruent angles. And that's it for our presentation.